to the webcast series Locker Talk, brought to you by BreachLock, a global leader in attack surface discovery and continuous pen testing and red teaming. Today's webcast is Behind the Breach, Web Applications and API Hacking, where we will discuss the transformation of modern web applications and demonstrate how attackers are persisting in uncovering and exploiting vulnerabilities despite advancements in technologies and new innovation. This is part one of a two-part series, and both part one and part two will be available on demand at the BreachLock website after this airing. Our guest speaker today is Mitchel Koster. He is the Chief Security Researcher at BreachLock. Before joining BreachLock, Mitchel worked as a red teamer at ING Bank, bringing expertise in hacking and software development. He holds credentials as both an offensive security certified professional and an offensive security certified expert. Mitchel leverages his expertise on the client side in software development and embedded devices to lead advanced penetration tests and drive cutting-edge research and security automation. Thank you for joining us today, Michael. Okay, thank you for joining us today, Mitchel.
Thank you, Anne. Nice to be here.
Okay, I'm going to say that again. I don't know where that came from. Okay, thank you for joining us today, Mitchel.
Thank you, Anne. Nice to be here.
All right, and with that, I am going to turn it over to Mitchel, and he will start the presentation.
All right. And the screen should be visible to everybody. So, welcome to part one of the two-part series of the Web and API Hacking workshop. So in this workshop, I will be covering web and API hacking, but more specifically, I will be trying to give an understanding of web vulnerabilities, how they work, how they are exploited, as well as how to prevent them, mitigate them, and patch them. Right. So in particular, this workshop will be around vulnerabilities that we see often on daily basis. Right? They might not all hold true to OWASP 10, but they are very prevalent, and above all, I believe they should no longer exist because they are trivial to patch and easy to understand. So let me move this bar out of the way. So to get a common understanding before we dive a little bit deeper into the matter, pausing for a second here to see if we can still see the screen. All right. So to build a common understanding before we dive any deeper into the matter, I think it's important to explain a little bit about the evolution of web-based applications, and not just the web applications themselves and how you use them, but also on how they are built, how exploits have changed over time, as well as our tooling and environment have grown with that. So the first era, in my view, is the Wild West of the web, right? This is mostly stands out because everything is custom code. You have to reinvent the wheel for everything. If you wanted to use somebody else's code in a project, it was not as simple as import this module and be ready to go. You have to find it somewhere online, import it, somehow hack it into your application, right? And then manually keep track on whether updates or not were coming out. And if you were lucky, there was a mailing list. Above all, nothing was standardized, right? So if you want to make a website, you had to make one version of the website for every browser, or sometimes even every version of a specific browser to begin with. For example, I once had to write, way back in Internet Explorer 7 era, had to write a simple form validation script that would just check if every form field had been filled out correctly. Internet Explorer 7 was revolutionary in the sense that it had a backwards compatibility button, so you could test as if you were on Internet Explorer 6 as well, by just toggling a button instead of having to deal with virtual machines with older operating system versions. So the problem with this was that after a day of writing the functionality, having tested it, I would get users come to me saying that it did not work because they were still using Internet Explorer 6, even though I had tested it for Internet Explorer 6 with the compatibility mode. As it turns out, right, the Internet Explorer 6 itself did not support for each loops yet, and they would only support for loops, whereas Internet Explorer 7 with their upgraded JavaScript engine would support for each. So even in the cross-compatibility layer, it will still use the more modern JavaScript engine. This is just to highlight like some of the problems you would have, and they were plentiful. So in terms of unique security issues in this era, right, like I mentioned, there's no standardization across web browsers, right, or way of coding things. Browsers themselves are inherently less secure. Stuff like tab isolation and sandboxing, meaning that if you were doing your banking on one website and watching your daily news on another website, but your daily news website had for some reason an infected JavaScript payload in there, they would now be able to access your banking data. This is the era of classic vulnerabilities, think SQL injection, browser takeovers, and really when the port entry was extremely low in web development. So recognizing these issues, right, came the rise of the more prominent development frameworks. The biggest upside of the frameworks is that they came with pre-built features. So instead of having to reinvent the wheel, like how do we communicate to the database, how do we manage authentication and all that, you could now rely on the framework to do this for you in a faster and more secure manner without having to write everything from scratch. Similarly, dependency managers made it easier for you to upload or to download new source code into your projects. Somebody else or a group of people contributes to a new feature, you can download it and seamlessly upgrade it, leading to less custom code overall and bigger supported projects by the community. What I mean by an example of development frameworks can improve security, I've taken the example here of PHP Laravel, a framework I'm more familiar with. They will have built-in security measures that will protect you against any form of cross-site scripting or SQL injection and all the classical vulnerabilities, as long as you adhere to the framework and you don't do anything silly, you are safe by default. So if code is getting safer here, then what is the new security issue that is introduced? In this case, with dependency managers, supply chain attacks like demonstrated image below are introduced. You're pulling code from somewhere. A lot of people are contributing to it. What if somebody contributes malicious code? Suddenly, all your projects might be insecure in one go. And with frameworks comes greater security, but also sometimes you have to deviate from the framework. So how do you now safely add custom code to a framework while still adhering to the framework best you can? If you don't think that supply chain attacks are very common, just the top few Google results from the last few years will show you very frequent attacks all over the news. So this is a real risk. The third era, I'd argue, is the era of stability, of scalability, and JavaScript, right? JavaScript having become the predominant web one language to rule them all. Whether you want to make a website that you can render in your browser, you want to build a desktop app like Spotify, you want to run your own web server, or you want to even create a mobile app, JavaScript can do it all. So as it's becoming easier to roll out applications across the entire landscape and it becomes faster to program with them, it comes at a cost often of speed, right? In an era where scalability is more and more required than ever, which leads us to really the perfect scenario for the cloud revolution. Right? You no longer have to worry about your code being as fast as it can be. So even if JavaScript might not be the most fast code in terms of resource usage, if you can endlessly scale it with the cloud, what does it matter? In addition to that, the cloud often comes with more safe defaults. You don't have to worry about managing servers and hardware. So it offers a lot of convenience. And even a lot of that nowadays is, managed through code as well. So what is then the problem? If everything becomes JavaScript and everything becomes API based, and a lot of client applications, client side issues become more prevalent. APIs often expose too much data, authentication between various platforms is not handled correctly or is generally very complex. And once you migrate to the cloud, suddenly you have to wonder, how do we manage source codes and secrets? If a cloud provider could theoretically, like in the case with Elasticstack, just take your intellectual property and make it their own, or what happens if the cloud provider decides that your company should no longer be on their platform? It is not without its risks in its own right, despite all the benefits. And then the last kind of current era where we are in, right, is where we have an era of primarily new protocols and databases. So everything that we know so far has primarily been on the HTTP 1.1 stack, right? And going forward, we see a lot of new protocols pop up, and we see a lot of new databases occur. Right, so the technology is changing, even though we're using the same stack, the technologies are changing underneath our eyes, and we have to keep up. So that's been a great history lesson, right? But what's the point to this? Historical does not mean extinct. All of these security issues that I showed you, even the one from the very first era, are still very prevalent today. We have a great amount of abstraction added to cloud infrastructure and frameworks that take a lot of the heavy lifting away and create more secure defaults. However, it also raises the bar for younger developers. We create an over-reliance on frameworks and traditional knowledge on how to secure software and infrastructure is rapidly disappearing with the increasing abstraction. So, what now we go to the real world vulnerabilities, right? Now we have the common backstory. We go to the real life use cases. Everything I'm about to show in this part, as well as the next, will be around actual vulnerabilities that we see day to day, anywhere ranging from a startup to very large enterprise clients. Everything will be showed using a modern development framework like you would use in your workplace, not on a really old dynamically typed minor application, although in this case we'd be using Laravel. And again, I believe these vulnerabilities should no longer exist. So if we do everything correctly, by the end of this workshop, you should wonder why, just why do these vulnerabilities still exist? Right, the first example I will be showing is an example of cross-site scripting, and not just the old vanilla style cross-site scripting, but one we see quite often that is missed despite security practices in place. And that's cross-site scripting through a upload of an SVG image. This is by far the example we see the most, that is most easily missed, and it can be patched in two means: by either on server level updating the security headers, or by patching the application code. I should mention, because a large part of this presentation is to convey the usefulness of programming frameworks, right? The programming framework I am demonstrating in its latest release a week or two ago has actually made it so by default in an upload, SVG images cannot be uploaded unless you add a deliberate exception to that. Right, just as an example as to how frameworks can help you become more secure. So this cross-site scripting attack will not just be any, it will show you how an attacker can take over your website and then essentially turn it into a keylogger and send the credentials back to an attacker. So it will take a few seconds to spin up the demo environment, after which you will be met with what represents a multi-tenant environment, imagining that every company gets their own unique login page where they are able to upload their own company profile image. And as you can see by now, we have the default little square thing up top. And if I were to replace it by a different image and upload it, all of them are SVG images, all valid. You can see it is now turned into a small chef's head. If I visit this in a private browser, you can see that the login portal has changed, or at least the icon representing the company. The problem here becomes when we start uploading images, SVG images that contain more than just SVG, that will contain malicious JavaScript in it as well. So in the first image that I will show you, I will show the source code as well. You can see a very minimal example with just a very basic JavaScript injection in there, which does nothing other than bring up an alert box to demonstrate the initial vulnerability, but not quite demonstrate the impact. This is particularly damaging because in this case, the image is public, right? So you could take a copy of this image, like I will show here, give this to any non-suspecting person, right? And you can tell it's still on the same domain. It just links to an image, so it doesn't stand out, and the virus won't pick up on it quick, neither with email filters. But if you send this to anybody, they would essentially be able to get phished from your domain. And of course, as I'll show here, the alert box is not very impactful, so we can improve the impact of this quite a bit. Here you'll see where I'll take my second example, and I will just walk through the payload on a high level so you can understand what's going to happen before you see it. What this payload does is it will create an iframe on the page. So you go back to the same image page, it will inject an iframe, change the title of the window, change the URL so it looks like it's the actual home page, and it will then start to load in the original login page, hijack the login form, steal whatever you're typing in, i.e. your username and password, relay that to the attacker, and then actually log you in. So you will be logged in as usual and none the wiser. And all of this, it will give the payload 6 seconds to take place. I'll show you it all working. So once again, after uploading, we can grab the link to the image. Pretend again we are sending this to an unsuspecting victim. And the first thing that should stand out is that the URL looks like it's the normal login page. We can see the login form, we can see the page title. But if we look under the hood, purposely for both, I made a message that says login form hooked, so we can verify that we are actually on our attacker controlled content. And now if I try to log in, again to be verbose, you'll see that the credentials will be siphoned off to the attacker once I start the attacking server. You get a warning again for display purposes. Look, your credentials have been stolen. You are logged into the application and can use it as normally. However, in the background, you can see that the attacker has received the credentials. So you could be phished and lose your credentials without ever knowing it. And in this case, 2FA would not necessarily be of much help. So now we come to patching these vulnerabilities. As I mentioned, you could patch them in two places, either through the security headers or on application level. And the first thing that we do on security headers is that we start to restrict here what is allowed and what is not, i.e. we're specifically starting to deny iframes, which is the biggest attack factor here. And the difference between the X-frame options and the content security policy, of course, is that with the content security policy, you have a lot more fine-grained control in what you do or do not allow. You will have to restart the web server for any of these changes, right, or reload it. And now if you try to do the same attack again, the bug might not be solved in its entirety, but it will not work in the same manner because your browser is no longer allowed to open an iframe on this domain. An alternative would be to force the images specifically to be downloaded instead of loaded on the website. So now if you grab the same URL again and you would send this to a victim, now they would get the image downloaded instead. And again, because the previous mitigation is in effect, you still can't open an iframe to the same domain. The final alternative on web server level would be to sandbox it in its entirety, meaning that the web server will try to prevent any malicious content from being filtered out. None of these solutions might be the total solution that they're looking for. They might be absolutely perfect. It will, of course, depend on your use case. So pick what's appropriate. And of course, the person conducting the pen test will be able to help you with this. So if we pick the image again, and now we look from a sandbox perspective, we see nothing is loading. And then finally, of course, we have the application level fixes, which is probably the easiest fix to do. I have a already secure upload controller built, and the only difference here in this minimal example is that I added a sanitizer library, which will try to filter out any malicious injections that we could possibly enter. Right? In this case, you won't need to restart your web server and it would instantly take effect. And now if we try the same thing again, you will see that it will not work. You can see the warning there that the image was blocked. And if we look at the very basic example we originally had, you can see the malicious code has been stripped from the content. The second vulnerability I want to look at is cross-site request forgery, a often misunderstood one. In this case, cross-site request forgery can trick an unsuspecting victim to have an attacker perform an action on their behalf, as long as they are already logged into a website, right? The attacker would use their session to do something. So in this case, I will demonstrate a website where you can modify your profile, right? And the idea is that the unwitting logged in user would then visit a advertisement controlled by an attacker. And the attacker can then use his session to the already existing website to update the profile on his behalf. What then happens is the attacker updates the email of the user profile so that you can then request a password reset of the user and take over his account. There's two ways you can deal with this. The first one is by adding CSRF tokens on forms, and there is multiple ways to do CSRF, but it's the most common one. And the other one is to apply a same site status to your cookies that is anything but none. All right, so I can fast forward a little bit through the setup of the environment. We will create an account again like before. And once we are logged in, you can now see that we have a profile modification page where we can set a username, reset a password, and change the email. And now we open a second browser, which represents the attacker. The attacker by default knows nothing. You have no access to the application, but you might have access to an email of somebody that you're trying to phish. Right? So the attacker would require some prior knowledge of the application, like how does the login form look like, in order to be able to carry out this attack. Right? What the attacker just did is that they host a web server, and as you can see in the client side with a advertisement, right? This mimics the user visiting your malicious advertisement. This can just be bought and sent out by the attacker in bulk, right? If they're targeting a popular website such as Facebook. And all that the user just did on the left-hand side is visit a web page which loaded the advertisement. Now, on the attacker side, we don't have to do anything. All we do is we know somebody clicked our advertisement or viewed it. We can now say, I want to ask for a password reset for hacker@attacker.com, even though we had no account on the website prior. If we look, we do get a password reset notification now. And if we reset the password to anything of our choosing, we can now log in with our email. If you pay attention in the top right corner, what you see is the user test. Despite us not owning that account or not having access to it prior, you can see the email has changed to hacker@attacker.com. And if you refresh the page in the client browser, you'll see the same. You are not logged out, you're not aware of any action being taken, you just visited a different website. So to fix this, is really made easy in most frameworks by default. In this case, even I had to purposely make this vulnerable. I had to take multiple steps, right? The first thing is that in the middleware of this framework already, you have to provide an exception from the CSRF protection, right? So in this case, in this example, if you want to perform Stripe payments, you would need to disable this, and this could be a justified reason to do so. But in this case, we also added our pages that we wanted to make vulnerable on purpose. The second thing that you would need to do is on every form that you create, you can add a specific CSRF tag. As you can see, it's already enabled on that form. And if I go to the other page that we just had, our profile update page, all I do is simply add the CSRF tag, and that is it. We are now fully protected from this attack. The second option was, of course, in the cookies. If we change our cookie settings so that it will always have the same site policy of at least lags, every browser is protected and not just Google Chrome. And depending on your framework, you might have to reset the configuration cache. And now, if from an attacker perspective, in this case, as the user, we set our password back to the original, we reset the scenario, we try the same attack again. I have to restart the web server that serves up the malicious ad. But if we try the same attack again, it looks like it should have worked. But if we go back to the user profile page and we reset, the attack did not work out successfully. And you can see now we get a different status code as well. Page expired because we simply cannot use the same attack because we need to know the token that has been added in secret, and we as the attacker do not know. And then the final one I would like to show for the first part of this workshop is the broken password reset, because this one is so common, again, with a very, very high severity and usually leads to account takeover of pretty much any user on the website. Often there's mistakes in how the password reset features have been implemented, as particularly around tokens. And I'll give a demonstration on that as well as how to patch. But in short, tokens should not be predictable and they should expire at some point and they should only be usable once. Hopefully this will feel a little bit familiar by now. We have to spin up the original environment, which I'll skip through for the sake of speed again. We set up a new account, so we have a user to originally test with. And the first thing we do is we try to do a password reset for the account we just created. If we look on the email server, we'll see a password reset link. And one of the first things you would look for as an attacker is to see if the token in and of itself is predictable. In this case, the token is a MD5 hash based on the email address of the user that asks for the password reset, meaning that as long as we know an email of a user, we are able to then also create a password reset link for that user. And then similar to the last video, with a password reset link, we are able to take over their account. So having logged in again, we now take any random user. We throw them in a script I've conveniently thrown together to demonstrate how easy it would be to exploit this en masse as well. And the script, just for clarification, really does nothing but take an email. Based on the email, create a token and create a password reset link as we've seen it before. So this would be enough to create a password reset link, but in order to use it, that I can predict the link doesn't mean it exists yet, right? So I have to, of course, first create a password reset for which you would get an email as the user. So it's not completely without notice. Now I can provide a password reset link without even having access to anything. I can set a new password for your account. And then of course I can log in as you, and your account is now mine. So to patch this, again, this is one of those things where I have to purposely break default functionality from the framework apart to get it to be vulnerable, which is testament to how good frameworks are. The first thing that you noticed is that I set a expiration time of 60 minutes, meaning tokens are only valid for 60 minutes. And the second one is that I limit the amount of requests that could be made for password resets, stopping mass password reset attacks. So I can't just do this for every user in the database in one go. The second one is that I had purposely had to introduce a weakening token generation, right? So that it would use a weak hashing algorithm like MD5. And as I'm showing here, in this case, again, the framework and most frameworks that are mature by default will have pre-existing means for this. So all I have to do here is just reinstate the original functionality instead of what I had created. And this will take a second. But once I have removed all newly added functionality, as you can see, I had to go through quite some hoops to get this to be vulnerable. It's almost impressive nowadays. Yet we see this all the time. Right. So now I can take another email address. Now everything should be patched. I can create a password reset token. I then, of course, again request a password reset link. I try to reset the password, and it will initially look like it will work because the interface will still show up. However, you can see here it's invalid because the token doesn't match what it should. And the framework will take care of all three issues I mentioned prior. It being usable only once, making sure it doesn't expire, and tokens can only be cannot be reused altogether. So far in the first part of this workshop, right, we have given a bit of a background into the vulnerabilities and mitigations, right? Where do frameworks add more security? How have browsers evolved, right? We have shown 3 vulnerabilities, and I think if nothing else, so far this first chapter highlights the importance of understanding your tooling. And I think what holds true for the second part as well, right, is with all this added complexity, knowing your tooling is one thing, but for junior developers, this can be really overwhelming, right? So you will always need senior people there to help them and to get familiar and to show them how things work underneath all of that abstraction. And that concludes the first part of this workshop.
All right. Thank you, Mitchell. So that concludes part 1 of this webcast, again entitled Behind the Breach, Web Applications and API Hacking. Again, I'd like to thank our guest speaker, Chief Security Researcher at BreachLock, Mitchel Koster. And again, this webcast will be made available on demand at breachlock.com after this airing, and be sure to watch part 2 to learn more. And if you would like more information about BreachLock and our offensive security solutions, please feel free to contact us at hello@breachlock.com. Thank you.